In this video, I will present two solutions to the Russian roulette problem, which is a classic problem in probability theory. For the solutions, I will be leveraging some material that I will assume as prerequisites. In particular, I will assume you know what the Kolmogorov's axioms are and the total probability theorem, each of which I've dedicated a video to on this channel. And for one of the two solutions, I will leverage geometric series, which is a basic result from single variable calculus. If you're not familiar with geometric series, I can suggest you to look it up on your own, or you can simply skip that one solution. Consider that two duelists, duelist A and duelist B, have a revolver with a rotatable magazine. The magazine contains 6 slots, and the duelists load it with 1 shot, as illustrated in the figure on the left here. After this setup, the duelists start taking turns, as described next. So first, duelist A rotates the magazine at random, points the revolver at his or her head, and presses the trigger. You can consider here that the rotation of the magazine is completely fair. In other words, there should be a 1 in 6 chance that duelist A dies on the spot. However, if duelist A survives, he or she then hands the revolver to duelist B, who repeats the first step. And then the duelists continue in this fashion over and over until one of them are dead. And the question we're trying to solve here is, what is the probability that duelist A dies? And before getting into solving this problem, let me just briefly discuss some intuition here. So firstly, I think one natural thought that might pop into your head is that it should be equally likely for either duelist to die. But if you think about the problem a little bit more, you'll quickly realize that this is not the case. Because since duelist A is starting, it must be more likely that duelist A is the one to die. So already from this basic thinking, we can get to a point of saying that the probability that duelist A dies should be over 50%, because for sure one of these two duelists will die eventually. Okay, with that, I would suggest that you pause the video here and try to solve it on your own. Next, I will present one of my two solutions to the problem. I'll start out by presenting what I call the naive solution. And by naive here, I simply mean that this is probably the easiest solution to think of, but it's quite inefficient in the sense that you need to do a lot of computation to get to the answer. So there is a more elegant solution as well. But I think if you try to solve this problem on your own, most likely you end up with the naive solution. So that's quite natural. So let me start here by defining some events. Let's say that we have an event S1, which is the event that the first shot was a kill. So this means that if S1 goes off, that means the game is over immediately and duelist A is dead. We can also say, just from the problem description, that the probability of this event has to be 1 in 6, because it's 1 shot out of 6 slots in the rotating magazine. And we can expand this generally to the events Si. And we're going to define this for all integers I, well, at least all positive integers I. And that is the event that at shot number I, there was a kill. And here we can say that if I is an odd number, that means that duelist A have died. And if I is an even number, then duelist B must have died. And let's try to illustrate these events a little bit. So if you go to the left here, we can draw a box. And I'll say that this box is the sample space omega. So these are all possible events that can occur. We change the color. And the probability that S1 happens within this box, as we already established, is 1 in 6. So let's say that's about a sixth of the area. Then now we can start to reason about the remaining events. Let's start with event 2. How big will it be? Well, first of all, clearly it cannot overlap with S1. Because if S1 occurs, then duelist A is dead, and there will not be a shot 2. The game is already over. So it must only operate within this box. And within this box, it must be another 1 in 6. Because now there's a 1 in 6 chance that the gun goes off again. Because there's no memory in the gun. Every time you shoot, there's a 1 in 6 that the shot goes off. Because they rotate between each shot, remember? So now we have S2 here. And then the same logic applies. So S3 must exist within this box, and it's now 1/6 of the remaining set. Now we go on like this, essentially, well, potentially for an infinite amount of time, right? And as I'm sure you understand, these events get progressively smaller because we're taking 1/6 all the time of a smaller space. Okay, a 6 is way too big. That's not a 1/6 of this space, but you get my point. So we can say already now, just by looking at this figure, that the probability of S1 is going to be greater than the probability of S2, and so forth. And we can also say that all of these events are mutually exclusive. So if you take any event I, and you take the intersection with any event J, then that is the null set, as long as I and J is not the same, right? So this we can already tell given these definitions. And that helps us a lot, especially the second one, because that's a condition for Kolmogorov's third axiom, and it's also the condition for the total probability theorem, which means that with these definition of events, we can potentially use either one of these two. At this point, I think we should express the event that we're actually interested in. And the event we're interested in, let's call it event A, namely that duelist A is the one who dies. And we can tell that, given our previous definition of these SI events, that this is going to be the union of all odd shots. Because if any odd shot leads to a kill, that must mean that duelist A is the one who died. And this will go on for an eternity. We can say S infinity here. And I'm implying here that we're only talking about odd integers, right? But I'm not going to formalize the math at this point. And from Kolmogorov's third axiom, we know that if you have a union of a bunch of events that are all mutually exclusive, then the probability of that union is equal to the sum of the probability of the individual events. So let's me type this out. So the probability that duelist A dies is equal to the probability of shoot 1 leading to a kill plus the probability of shot 3 leading to a kill, and so on. And now we can formalize the math a little bit. We can say that this is, of course, a sum that starts out at 1, it goes up to infinity, and we're interested in the probability of S. Note that I cannot just write I here, because that would also include the even events. So we'll write 2I minus 1. Okay. So this is Kolmogorov's third axiom. So here we're using Kolmogorov. Okay, so can we compute what the probability of a general event SI is? That's what we're going to try to do next. I think the easiest way to do this is to go one by one. So we start with S1, this we already know. Then we go on to the probability of S2. Well, as we mentioned before, S2 can only happen if S1 did not happen. So we start out by saying that it must be the case that S1 did not happen. I use this apostrophe here to indicate that this is the conjugate of the event, or the probability that it did not occur. And after S1 did not occur, we now have a 1 in 6 that the bullet actually went off the second time. What is the probability of S1 prime? Well, that's going to be 5 in 6, right? Because it's just 1 minus the probability of S1 times 1 over 6. Okay, then we continue. S3. Now it gets a little bit trickier, but it's the same idea again. So first of all, S1 must not have occurred, right? Because otherwise we would not be at step 3 right now. Duelist A would already be dead. Then here is why I say it's a little bit tricky. Note that it's not just the probability that S2 did not occur, but it's the probability that S2 did not occur given that S1 did not occur, since we have the probability of S1 conjugate here. And then if S1 did not happen, if S2 did not happen, then it's now a 1 in 6 that S3 is going to happen. Okay, what are the probabilities here? This you already know, it's 5 in 6. Here, let's think for a second. Okay, so we know that S1 did not happen. If S1 did not happen, that means that there's still one shot in the magazine. Now duelist B takes the gun, pulls the trigger. What is the probability that duelist B does not die? Must be 5 in 6, right? So once again, it's 5 in 6. And then the gun must go off. And now we start to see a pattern, right? This is 5 in 6 times 5 in 6. That's 5 in 6 squared. And this is just 1 in 6. And at this point, I think we're ready to generalize. So we can say that the probability that Si happens for any integer I is equal to 5 over 6 times the power of I minus 1, because event 3 has a 2 here, event 2 has a 1 here, event 1 has a 0 here, multiplied by 1 over 6. Okay, this formula we can plug straight into here, and that will help us to compute P of A. But we'll do that on the next slide. Okay, so as you can see here, I've copied over the results from our previous work. The only change I made is I replaced the variable I here with the variable n. And the reason for this is just I don't want to have the same variable in both of the two equations. That's going to get a bit confusing. Okay, but essentially we have the answer here. And we've done all of the hard work. Now the only thing that remains is computation. Because what we want is P of A. That's the probability that duelist A dies. We know it's a sum of some events, and we know what is the probability of all of these events. So at this point, really you could say that all the probability theory work is done, and all that remains now is a little bit of calculus. Okay, so let's do a variable substitution. Here we have 2i minus 1, here we have n, so let's say that n is going to be equal to 2i minus 1. Then what will this probability become? Well, we still have this 5 over 6 here. Up here we have n, which is 2i minus 1, minus 1. So there's another minus 1 here. And then we multiply this by 1 over 6. Now, if you're familiar with geometric series, this will look very much like a geometric series to you, but let's massage it a little bit to make this crystal clear. First of all, we can see that this is 2i to the minus 2. So we can change this expression to look like this, where we say that this is 5 over 6 to the power of 2i multiplied by 5 over 6 to the power of minus 2 multiplied by 1 over 6. Why did I do this? Because now it's clear that this is constant, so we can just move this outside the sum. Right? If we move that outside the sum, well, this will become 25. This is 6 squared. So we're going to have 6 squared divided by 25 times 1 over 6. And we have the sum. And the only thing that remains inside of our sum now is 5 over 6 to the power of 2i. And we can do some further simplifications. We have a 6 here, we have a 6 here. So this is going to be 6 divided by 25. We're going to take the sum. And since it's customary to just have the variable here without a factor, let's just compute the square. So this is 25 divided by 36 to the power of I. Now this is kind of the classical geometric series. If you search for geometric series on Wikipedia, probably it will look exactly like this. Maybe it will look like this, but you can just substitute A and R, and you will get exactly the right answer. And also a condition for the geometric series to converge is that the absolute value of R is less than 1, which is clearly the case here, right? So at this point, we are completely done. I'm not going to do the computation because it's not probability theory, it's just calculus, but I just give you the result. This is 6 divided by 11, or approximately 55%, which matches up with our intuition from the start, right? Because we knew that it was going to be more likely that dualist A dies than dualist B dying. So essentially, by starting this game, dualist A is incurring a penalty here, more likely losing his or her life than the opponent. Okay, so just to quickly recap, essentially the only thing we needed to do here was to define a set of mutually exclusive events. And since they were mutually exclusive, we could leverage Kolmogorov's axiom to compute the union of them, which was P of A, the event we were looking for, or the probability we were looking for. And we also had to find this general formula for all of these events that we defined, which was basically done by intuition and a little bit of conditional probability. Okay, next I will do the much simpler and more elegant solution before I close off the video. So for the elegant solution, I'm going to start the same way that I did in the naive solution, namely by defining some events. Actually, we'll use more or less the same events, but we'll have one new one. So we'll keep event S1 from before, namely that shot 1 results in a kill. And then we'll keep A, namely that dualist A dies, and B, which is the new event, which says that dualist B is the one who dies instead. And let's quickly draw the sample space like we did before. But now we're not using this infinite series of S1 events, but rather we can use just these 3 events that we've defined here. So to start off, S1 is 1/6 of the space like it was before. And we can just say that the remaining part here is just S1 conjugate. Of course, the event plus its conjugate is the whole sample space and it's mutually exclusive. So it has the same nice properties as before. Then we look into A and B. I guess I'll take some colors here to illustrate it. So let's say that A is red. We can say that if S1 happens, then for sure also A happens. Because if the first shot is a kill, then A dies immediately as soon as the game starts, right? So all of A1, and then some subset of S1 conjugate. We don't know what this subset is, but we know for sure that there's some non-zero part here. Because shot 3, shot 5, shot 7, etc. are all in S1 conjugate, and they all lead to dualist A dying. Then we need another color. Let's take purple. So B is now this remaining part here, and it's entirely contained within S1 conjugate. And of course, there's no overlap between these 2 parts because dualist A and dualist B cannot die simultaneously. So again, we have another set now of mutually exclusive events that cover the whole sample space. How can we use this? Well, the idea here is that we can use the total probability theorem to compute the probability A that we're interested in. And we'll do it over the events S1 and S1 conjugate, which cover the entire sample space. Okay, so let's write this out. So remember, the total probability theorem says that if you want to compute the probability of any event, you just need to compute it conditioned on events that cover the sample space. So we're saying here that this is equal to probability of A conditioned on S1. And here, then you must multiply by the probability that the event you're conditioning over actually happens. And then you keep going like this until you cover the whole sample space. In this case, it's very easy because we just need 2 events. So we just say that this is the case. Okay. And that's it. So this equation is just a statement of the total probability theorem. So there's nothing magical here. We already talked about this in another video. Now, what can we compute here? This is pretty simple. If shot 1 occurred, what is the probability that A died? Well, that's 100% because the first shot is always shot by duelist A. What is the probability that the first shot is a kill? That's a 1 in 6 because of the setup of the problem, right? Then on the right, this one is a bit tricky, so I will leave this for the moment. And then this one here, this is the probability that you're in the conjugate so that you miss the first shot. That's a 5 in 6. Right? Okay, so now we have to get a bit clever here. What is this event? So we're conditioning on the fact that S1 did not occur. So what does this mean? That means duelist A took the revolver, pointed it at its own head, pulled the trigger, no shot came off. Player A handed the gun over to duelist B, and now duelist B is sitting there, gun pointed at his or her head and about to pull the trigger. What this really means is that we've just restarted the game, right? So now we're playing the game again, but there's one change. And that change is that player B is now starting. And note that if we're existing in this conjugate space here, then it's as if nothing happened apart from the starting order, because there's no memory in the gun, right? Every shot is completely random without any memory of the previous shots. So we're now playing the game again, but from the perspective of player B, in the sense that player B is now starting. And if player B is starting, what is the probability that A dies? Well, that's exactly equal to the probability that player B dies in the normal game, right? Because now we have reversed their roles. So we can say that this is 1 in 6 plus the probability of event B times 5/6. And this insight, this translation from this conditional event down to probability of B, this is really the thing that allows us to solve this problem. And now it's actually surprisingly easy, because what is probability of B? Well, as we showed up here, it's mutually exclusive with A, it covers the sample space. Therefore, it must be 1 minus the probability of A. Let me reorder things a little bit here. And what do we have on the left here? It's probability of A, right? So this is now one equation with one variable, probability of A. We can solve this. Let's change colors. So we're saying that probability of A is equal to 1/6 plus 5/6 minus 5/6 times the probability of A. We can just move this to the right. We can sum these up. And that tells us that 11/6 P of A is equal to 1. What is this? Well, you just take the reciprocal of this fraction, and we see that P of A is 6/11. And this is, of course, exactly the result that we got with the naive solution. So you can see here that by viewing the problem from this different perspective and by leveraging the total probability theorem, we can get to the same result with way less computation. In fact, if you use the scientific measure number of PowerPoint slides, we required 1/3 as many slides, right? So that's a huge improvement. That takes us to the end of the video. I hope you enjoyed it. You found something interesting in it. And if you're interested in more probability theory, I can recommend you to check out some poker problems. For example, if you do something like compute the probability of drawing a full house from a random deck of cards, that would involve some of the combinatorics that we explored in the video on earn problems. the urns, I mean these urns with balls of different colors. Then I'm also planning to make 9 more videos after this one. We'll see how long it takes. I tend to be quite slow since I work full time, but hopefully not too long. And of course, as always, I will recommend the book by Gunnar Blom, which I use as inspiration to make these videos. Okay, I hope you have a great day, evening, or whatever time it is that you're watching this video. Bye-bye.